Hello everyone, and welcome to our first video on the use of polymer molds in plastic injection molding. For this series of workshops, we've come to Metz, and more specifically to Blida, where HoliMaker's facilities are currently located. Blida, for those who don't know, is a place of inspiration, innovation, and collective intelligence, which has enabled HoliMaker to launch itself on the market thanks to their incubator. HoliMaker is a French company founded in 2009 by Aurélien Stocky and Vivienne Salamone, whose mission is to democratize access to plastic ingestion technology. But who better than HoliMaker to tell you about HoliMaker? So let's meet Vivienne in his workshop to find out more about this young French company. At HoliMaker, we design and manufacture in France, at our Metz site, solutions that groove plastic materials and melt them before injecting them into molds, all by hand. The solutions we offer are used by our customers for various purposes. Firstly, for prototyping, in the product development phase, then by plastics manufacturers to characterize and test their plastics prior to large-scale production. They are also used to introduce the public to simple plastic recycling, and then there are those who use it for small-scale production. But in fact, I'm talking about plastic processing, but Thibaut, we should first explain what is plastic processing, so we're going to see Aurélien, who's going to tell you all about it.
So, to explain to you how to go from an idea to a plastic injected object, you first need to understand how plastic injection works. We'll deal with the subject as follows. First, we'll look at the whole concept of plastic injection molding, so that you understand how we got from an industrial injection molding machine to an injection molding machine that fits on a work surface. Next, I'll explain the difference between a thermoplastic and a thermoset, which will give you a better understanding of how materials behave when injected into a mold. Then we'll finish off with a look at how a plastic injection mold works, and the criteria you need to take into account when designing a printing mold. The basic principle of plastic injection molding is to heat the material, knead it, and inject it by pushing it into a mold of the desired shape. In the case of a screw-type plastic injection molding machine, the raw material, usually in granulated form, is inserted into the injector via the hopper, then driven and heated by the combination of this screw and heating elements. Once the material has been mixed and melted in the heating chamber, the injector moves the screw to inject the material into the mold, acting like a piston. The part then cools in the mold before being ejected. There are several parameters involved in this plastic injection process, namely injection speed, injection pressure, injection temperature, holding time, and cooling time.
So Aurélien, explain to me how you went from an industrial injection molding machine to this.
Well, this, as you say, this is the HoliPress, and it works in a similar way to an industrial press. First, you insert the material into the heating chamber via the hopper, with a special feature in that the HoliPress is limited to a 16 cm capacity. Depending on the material selected, you set the temperature on the thermostat to heat the material without burning it. Instead of a screw, a vertical piston is used to inject the material at the moment of injection. The material needs to be heated to a certain temperature, and for a certain time to be injected correctly, you define the pressure and speed with which the material is injected by lowering the lever to inject the molten material into the mold. At HoliMaker, we've taken the historic plastic injection process and made it more efficient without complicating it. With HoliPress, it is possible to control its parameters. Injection speed is simply obtained by counting. Injection pressure is obtained via the user's feedback. Injection temperature is obtained via the control box, and finally, holding time and cooling time are set by a timer.
Thermosets and thermoplastics are two different families of plastics that differ in their behavior when exposed to a heat source. How can you tell them apart? Quite simply, thermoplastics are materials that soften under the action of heat and harden when cooled in a reversible manner. Take a chocolate bar, for example. If you heat the chocolate, you'll obtain a liquid consistency which you can then pour into a chocolate egg mold. If you want to turn your egg back into a chocolate bar, all you have to do is melt the egg again and pour it into a chocolate bar mold. That's how thermoplastics work.
Thermosets are the opposite of thermoplastics. They are polymer materials that can only be used once, and once polymerized, in other words hardened, they take on a shape that can no longer be modified.
To illustrate this idea, let's take a cake recipe as an example. You'll need to mix several ingredients together to make the batter. Then you heat them in an oven or with a catalyst to obtain your cake. In that case, unlike a thermoplastic, you won't be able to separate the different elements after baking. In our case, we'll be talking mainly about thermoplastics, and we'll tackle the subject of thermosets in a later episode. Did you know that molten plastic is 10,000 times more viscous than water? So you can't just pour it into the mold and have it fill the cavity, you have to exert pressure to inject it. With liquids, the narrower the pipe cross-section, the greater the velocity and pressure at that point. If there are obstacles, such as rocks in a stream, turbulence is bound to occur. A thermoplastic in its molten state is very specific. Plastic behaves like lava. The ends of the flow will cool into a solid range, while one of them, still hot, will advance and uncoil on the following walls. As the plastic cools, the molecules rearrange themselves, slightly reducing the injected volume. This can lead to shrinkage, which are lacks of material in certain places, but also changes in the shape of the part, known as warping. To avoid these problems, you need to know the percentage of material shrinkage and inject to compensate for it in the mold. Apply a scaling factor to slightly enlarge the print so that the final part can be the right size. But also dimension the part appropriately to avoid excessive cross-sectional changes, for example, or add ribs to reinforce the part's strength. To illustrate what a thermoplastic polymer is, let me introduce you to the most common materials. There's HDPE, also known as high-density polyethylene, found in water bottle caps, for example. PP, also known as polypropylene, is the most widely used plastic. It is highly resistant to chemicals and very easy to process. It can be found, for example, in this plastic crate or this product cap. PA, also known as polyamide, of which Rislin is the best known, is a plant-based plastic used to make cable ties, for example. It has excellent flexural strength. TPU, also known as thermoplastic polyethylene, is a flexible material used to make shoe soles, parts of toothbrushes, and technical seals, for examples. Many materials can also have additives in solid form, such as composites. A PP or PA reinforces a fiberglass or flax fiber, but also other additives to make UV filters, flame retardants, and so on. To explain how a mold works, imagine the mold of a waffle iron. The waffle takes the shape of the waffle iron, but also its surface finish. The finish of the piece will therefore depend on the finish of the mold. So for example, if you use FDM technology to 3D print your mold, the injected part will have a surface finish similar to that of FDM, so you will see the layers. If you use SLS technology, then you'll have a porous surface finish of your part. So, as with a waffle iron, the injection mold is a two- or multi-part element, into which molten material is injected before cooling and then being ejected. Ejection generally takes place via ejectors, which are mechanically actuated by the mold when it opens. In traditional plastic injection molding, the mold is usually made of steel to withstand shorter injection cycles and higher injection pressures. It can also be made of aluminum for prototype molds. And on the subject of this workshop, molds can also be 3D printed in SLA technology or LFS for Formlabs to obtain molds with a surface finish close to that of plastic injection. A change in thickness can lead to different cooling times, resulting in part warpage or shrinkage. So it's important to homogenize the different thicknesses of the part you're designing as much as possible. To avoid the phenomenon of shrinkage, make your parts hollow as much as possible and add ribs from 0.4 to 0.7 times the thickness of the connected wall. Don't forget to strip the ribs. As much as possible, the wall thickness of your part should be between 0.6 and 4 millimeters, depending on the material you're going to inject. The minimum thickness will naturally depend on the material injected, as well as the material of the mold used. Remember to add as many fillets as possible to the part to limit breakage, damping, and turbulence during injection. Part made by plastic injection must be ejectable after injection. In other words, once the part has been injected, you need to be able to remove it. To achieve this, we use what are known as draft angles. This is an inclination of the mold wall similar to that found on cake molds. To achieve this, drafts must be designed in the direction of part ejection. They must be at least between 2 and 5 degrees, and the greater the inclination, the easier it will be to eject the piece. Please note that some objects, by function, may also require undercuts. Undercuts mean that you can't remove parts from the mold using ejectors. Side actions or inserts will have to be used. For example, this mold with side actions, or these inserts which have been made on this mold. Note that it may also be necessary to use release agents to facilitate ejection. Yes, you can perfectly well inject plastic into a mold to overmold elements, for example metal parts, to make chips, cables, magnets, or you can make bottle openers.
There are lots of metal parts you can overmold. You can also overmold plastics, for example TPE on another plastic to make this type of toothbrush, or TPE on this plastic screwdriver handle. So in fact, I think that 3D printing is rather complementary to machining. When we want to validate a project, using 3D printing speeds up the various iterations we will be able to carry out in plastic injection molding, while reducing the risks associated with the expense of launching a new pilot mold on a project. For example, for this remote control mold or this bottle opener mold, we used a metal machined mold, but with printed inserts to enable us to customize the mold between different productions.
To sum up, injection molding is the process of melting thermoplastic materials and injecting them using a press or mold. The plastic material is softened by a heat source and then injected into the mold, which then undergoes a cooling phase to create my final part. As for the molds, you produce them with thermosets. This is the subject of the next videos in this workshop, how to validate a design with 3D printing before going into production. Thank you for watching this video with us. To find out all about the design, validation and production of a mold, I'll see you in the next video. Thank you and see you soon.